Hello and welcome to the next video here. So we're looking at electric power. We already know what power is based on the main concept, right? We know power is energy per times the rate of flow of a transfer of energy. So we know it's in watts, right? We know that already. And so we look at energy to do with electricity. What's the concept to do with energy with electricity from the previous lesson? We saw that was to do with voltage, right? So the voltage is energy per coulomb, right? So if we start with the voltage formula, then we at least have an energy concept to do with electricity available to us. And so we can solve for the energy, of course, right? So we get energy, the amount of energy flowing or transfer of energy is the number of charges that went from A to B or flowed through the system times the voltage. And then if you know that you have current as a concept in electricity as well, you've got the amount of charge flowing over a certain amount of time, right? So the number of charges flowing is your Q. So we're going to solve for time here. And so basically we're going to be able to do energy divided by time, right? That's what we want to do, right? So we can go ahead and do that. We can do energy divided by time, which can be QV divided by Q over I, invert and multiply, and the Q's cancel out, and you just get a nice simple formula that power equals voltage times current. So the power in electric, in watts for an electric circuit, like a 60-watt light bulb, and so on, is just the voltage times the current, right? So for a 60-watt light bulb, the voltage, let's say the voltage is 120, some people say 110, depending on what kind of version of the voltage you're talking about. We'll talk about that a little bit more later, I think. But yeah, so we have the 60-watt light bulb would be 120 volts times obviously 25, so it would draw half an amp of current. So we'll reveal that equation. That's really nice and easy to develop. Literally just look at the concept for power being energy per time, and then solve for energy and time from two electricity equations that we know so far. So there's the third one that we know, right? All right. So which one has more resistance then, as a thought question here? A 60-watt light bulb or 120-watt light bulb. So I think a lot of people would think that this one would have more resistance, because just having resistance sounds like it'd make it be more powerful. But if you think about it, we're going to solve for it here. So let's just do that, I guess, right? We have a power of 60 watts, and so we get that half an amp, like I just reasoned out. If you weren't following that, that should be easier now to follow. We have our power, electrical power equation, plug in the power rating and the voltage, and you can solve for what amperage must obviously flow through it. And so this bulb would have a particular resistance that would allow this amount of current to flow. You want to know how much resistance? Well, we can use Ohm's law, right? We know the voltage, we know the current, we can solve for what the resistance is. So this thing has 240 ohms of resistance. Now for the floodlight, right? This one here, are you getting the idea of what this would need to be? This is letting 0.5 amps go through, so 0.5, half a coulomb every second is flowing through. Out of those coulombs are each carrying 60 joules, right? If you want more power, then each coulomb is carrying 120 joules, pardon me, right? If you want more power, you want more energy per second to go through, you're going to have to let more electrons go through, more coulombs of electrons go through, right? So we'll see that as a result here. We have 120 watts now, and the same 120 volts. And so it actually lets through twice as much current. It lets through 1 amp. Okay, and so then what's the resistance to let that 1 amp through? Well, obviously it has to be less to let more current through. That's what resistance tries to stop current from going through, right? And so, yeah, we can just solve out, and it's 120 ohms. So it's less, it's half as much. Okay? So there's less resistance, so it'll let more current flow through, which then, of course, allows more energy to be delivered, because each coulomb is delivering a specific amount of energy, which is what we call the voltage. All right, so I hope that's starting to make sense. That's what these things are. The weird thing about this unit is you've probably heard of current and voltage and so on, but just didn't really know quite what it was in reality. So now we're putting a face to the name, so to speak, here. All right. Based on that knowledge, if you were to wire up a cottage 12 volt, I'm not sure too many people do this anymore with inverters and all that we have, but it was common to do back in the day, so to speak. Would you need thicker or thinner wires? And I think a lot of people would think that you could get away with thinner wires because it's only 12 volt, right? So it's not that dangerous. But in order to provide the energy that's needed for things, right, you're going to need 10 times as many coulombs to flow, right? You're going to need more current. If you need more current, then you need thicker wires to be able to carry that current. Carrying current is difficult for wires, right? There's friction. Think of it as friction, at least anyways. And electrons like scraping their way through the wires. You need a larger hallway to allow more people to flow through it. You need larger wire to allow more coulombs to flow through it. Very easy way to think of it, right? So there are 60-watt bulbs you can buy that are designed to be used in a 12-volt circuit. So what would be different about that bulb? It would say 60 watts on it, but it would say 12 volts, hopefully in bold letters or something to let you know that it's different. Another clue that it'd be a different type of bulb is it's probably like 10 times the price as the regular bulb for household use. So obviously they sell more of them, right? So economies of scale, you have to charge more for something you don't sell much of in order to make it worthwhile to make it. So we have 60 watts, 12 volts. Obviously, we can use the power equation, right? So we can get the current, right? And then once we get the current, then we can get the resistance. So let's do that. Right, so we got our power and our voltage plugged in. We can get the current. It has to let 5 amps flow. It has to let 5 amps flow. And so we have 12 volts. We have to let 5 amps flow. This thing only has 2.4 ohms of resistance. Okay, so it has much less resistance to allow more current to flow. Okay, notice that it's 2 factors of 10 less, right? 1 for each. So you have to have a factor of 10 less for the current, but also a factor of 10 less for the voltage, since the voltage is only 12 volts instead of 120. So if you were to try to use a standard 120 volt, so you just plug in a regular bulb at the cottage you've got wired up, what would happen? So if you want to use a regular bulb from the hardware store, you would need one that has lower resistance, obviously, right, to have a chance of it working at all. And so you would want to grab the highest wattage bulb you can find, right? So if you find a 300-watt household floodlight, it might work like a regular 40-watt bulb or something, the way the math would work out, right? So this is not field yet, I suppose. So let's look at the idea. What if we used a regular 60-watt bulb, right? We know that the resistance is 240 from previous work, and so the current it would let through would be 0.05 amps, right? And each of those would only carry 12 joules, so way less current and way less energy, right? 10 times less current, and each carrying 10 times less energy. So the power you'd get out of it would be really, really, really low. It'd be very dim. You might not even see it glowing. So if you were to use, oh yeah, it's a special watt. Oh yeah, if you use the cottage bulb at home by accident, what would happen? Well, that less resistance is going to allow a ton of current to go through. You're going to blow a circuit or blow the bulb, whichever happens first. But it would try to let 50 amps go through. And your circuits are protected where they only allow 15 to 20 amps in your house, right? So circuit breaker would blow or the bulb would blow. But if it was able to let the 50 amps go through, each coulomb would carry 120 joules. The thing would try to function as a 6,000 watt bulb, 2 factors of 10 bigger. Okay, that's just how it works. So electrical devices are designed, obviously, as you can see here, designed to have a certain resistance. They call it internal resistance, right? So it's designed to let a certain amount of current flow so that it'll behave the way it's supposed to behave. So if you look at Europe, they have 240 volts rather than 120 volts. And the reason for that is because North America was wired first. Switches weren't great. They didn't want to have fires. There was sparking and sparking. You know, ever sometimes you flip a switch in your house, you might hear a little electrical flash or a spark or whatever. It's inside of a metal box, so it's not bad, but sometimes a little bit of dust gets in there. You know, so switches weren't great, and so they used 120 to keep it as safe as possible. Europe was wired a lot later on. All the big developments happened in North America. The new land, the new possibilities that people. It's just the way it worked, right? People traveled to North America, and they tend to be new kind of thinkers, right? New world. Just historically, the way it's gone, even the iPhone was, really major developments kind of still continue to happen in North America, and then Asian markets make it better. But anyways, so they basically scientists suggested they run 240 volt instead, right? So what would happen if an electrical device from Canada was just plugged in? Well, just like this, right? We plug in something that's designed for use in lower voltage. It's going to try to produce way more power. So say you took a hair dryer. So I have a hair dryer. I'm going to show you a video of it in a second here. But you have a hair dryer. It's supposed to be working at 120 volts, and it's listed as a 1200 watt hair dryer. Well, that means it's going to try to let 10 amps through. 10 amps is, like that's a good half or 2/3 of the energy that or amperage that a household circuit can carry. So you might have found out in your life at some point you can't plug in like 3 hair dryers or even 2 hair dryers at once in a house on the same circuit. Kitchens have separate circuits for every single plug, right? So you can plug in a toaster and a microwave and a kettle and so on in a kitchen. But you can't do that in your temporary kitchen in a living room if you're doing a renovation, right? So we have one circuit in there. Anyway, so 10 amps. So the resistance is 12 ohms for this hair dryer. So in Europe, if you plugged in that 12 ohm unit, it would allow 20 amps to flow. And then each of those 20 amps, so it's twice as much, right? Each of those 20 amps would carry twice as much as well. And so it would try to behave as a 4,800 watt hair dryer, right? So if you're using an adapter and all it's doing is adapting like the wire plug type, but it's not changing it, transforming it. That's something we'll learn about later about transformers. But if you're changing the voltage from 240 down to 120, then it would behave like normal. But as this stands, this thing is going to try to pump out 4 times as much as it's supposed to. It's probably going to melt or catch on fire or blow an electric circuit, right? So if you use an adapter, you're fine, right? This hair dryer that I have has a little switch on it that it has a little switch, so it's ready to go, to Europe. So here's the hair dryer, and so hopefully you can still hear this. Hey everybody, so here's the little hair dryer that I have. It has low setting, high setting. So just in case you can't hear that, so it goes to a low setting and a high setting, right? Here in Ontario, and I'm just going to change this little switch here. I do this one-handed, change this little switch. Pause here for a second. Change this little switch here that moves it. Right. Might be able to see in there it says 250 or 240 now. 250 it says. And so what did that do? So basically this makes it so it's safe to plug this in Europe or in a place where there's 240 volt instead of 110 like we have here. 110, 120, there's different numbers quoted, right? Anyways, let's see what happens. So the low still works, and then the high, all it did was physically lock out. I got just enough Wi-Fi to be able to play that one, I guess. Close that out and turn off the hotspot here. All right, so yeah, all it does is just physically locks it, so you can only put it on low, right? Well, in low power, it's going to operate much more powerful, right? So in low power, I think it only runs at like 400 watts or something. And so then you multiply that by 4 and you get, you know, an appropriate amount of power, or even less, whatever it is. So, you know, if you picture plugging in any device, you know, your phone or any other device without a proper transformer, it's going to try to operate at a way higher power setting than it's supposed to, and so it's going to fry. So have a fire extinguisher handy if you don't follow that advice. Yeah, not a good idea. So other weird little question for you here. What happens if a 100 watt bulb and a 100 watt bulb and a 60 watt bulb are connected in series? What would happen? Which is brighter? Well, the trick is to recognize that if you're hooking up in series, that's not normal. That's not how you hook up, you know, a 100 watt lamp and a 60 watt lamp in a living room. They'd be hooked up in parallel, so you'll both be getting full voltage. But these are going to share the voltage, right? And they're going to share the voltage based on or related to in proportion to the resistance, right? And so this one's going to have higher resistance, or sorry, the 100 watt bulb is going to have lower resistance to allow more wattage to go through. 60 watt bulb is going to have more resistance, and so it's actually going to be the brighter one. So I have a mystery circuit that I show exactly that, but you know, just don't have a video for that one handy right now. But there we go. So something that's neat is the CSA tags for all devices in Canada. Canadian Standards Association, something like that. I forget what it stands for. But yeah, CSA tags have a listing of information about the electricity, you know, uses and requirements and so on. And the neat thing is that they're always missing one little piece of information, right? So this one you can see it lists the voltage and the wattage and doesn't list the amperage, right? So we can figure out the amperage. And we can even figure out the resistance that this microwave has. That when you plug it in, the resistance overall that the electricity from the wall feels or sees or whatever in the microwave would be 24 ohms when it's operating at full blast. So there's a little calculation you can always do. Right? So this is just a power adapter from a laptop, and it says in there 120 volts, and it's using 36 watts for the input of it. Right, and then even the output has 18 volts and 1.5 amps. So the wattage it's putting out isn't given, and the amperage it's drawing isn't given, but you can calculate both of those things. And we can even relate it to efficiency, right? So we calculated that it's putting out 27 watts, and you're like, oh, so it's 75% efficient. You notice these things get warm, right? So even just leaving it plugged in all the time, you're using like 25% of the power that it's designed to put out. Right? So all devices, computers, kettles, you know, all along the way. This kettle, you can tell, you can calculate uses 12.5 amps. If it's 1500 watts and it says it runs at 120 volts, that's the information that's given there. They don't give the amperage for some reason. I don't know why they don't just give all of the information. Sometimes they give the wattage, sometimes they give the amperage. It's a strange, I don't know why they do that, but it's neat, it's interesting, it's good for me as a physics teacher, because I feel like, you know, I can give an assignment to my students to go and find, you know, the CSA tags on 3 different devices and calculate the missing information. Right, so this dehumidifier doesn't give the wattage, but it gives the amperage it draws. So you can calculate the wattage. Okay, so just kind of neat. To do with the cost of electricity, you know, you kind of, if you didn't hear about the way that electricity is metered out in Ontario after being in a physics class, we kind of missed something there, right? So the meters used to look like this. Now they're like digital, right? So I used to show how to read the meter. That's kind of obsolete, but it was all about the rotation of these things. And so this would be a 9, and then this would be 0, and then this would be a 1, and a little bit beyond. You can tell it's 1, and then it's only started counting here, right? So as this goes all the way around, this one will go to a 2. Anyways, so the way energy is delivered, delivered in energy units, but if we deliver it as joules, you know, when you have 1,000 watts running for, a kilowatt. So let me backtrack here. They sell energy by units called the kilowatt hour, and the kilowatt hour is how much energy is transferred to a system with 1,000 watts, so a kilowatt, is operating for an hour, which is 3,600 seconds. And so really they sell energy in chunks that are 3.6 million joules, so 3.6 megajoules, right? That's what the number is. And so their attempt at the time, the reasoning at the time for creating this like combined made up unit of kilowatt hours was they didn't want to sell by joules, right? Because they didn't want to be selling like such large numbers of joules, but really the metric system was just sold it. It's like didn't have to create this kilowatt hour nonsense. But it is what it is. They sell, at certain rates of, so we have this tiered pricing and so on. So if you're on peak, you're going to pay, back in 2014, it was 13.5 cents per kilowatt hour, and it jumped up to 18 cents per kilowatt hour, and then the prices changed over time. So an electrical energy example here, we have 5.5 amps at 240. You're using this many kilowatts, and then if you multiply that by the number of hours you used it for, you can get the number of kilowatt hours. This is a rate of flow of energy. This is an amount of energy. So if you're looking at the cost of something, you just multiply it by the number of cents per kilowatt hour, right? So that is our unit, or our lesson on electrical power. Hope that works for you. And if you need any help with solving circuits and so on, we can do some more videos of that as well, but and post in the help section. But that is the next topic. So your new equation, power equals voltage times current. It's just another relationship that exists between the concepts that we're learning about. So I'd encourage you to recognize them as actual concepts rather than just letters, right? P equals VI, and the P is this, and just think of it as power equals voltage times current. Why does that make sense? Well, because voltage is energy per coulomb, and then current is coulombs per time, and so you're getting this combined unit where you're getting energy per time, right? So to itemize that out, I can do that right now for you here, where you have the voltage is joules per coulomb, and then that's this one. Right? I should color code here. So that's that one, and then the current is coulombs per second, right? And so you're ending up with I should have used a Q there for coulombs, consistent here, but when I do the units version of things, let's do that actually. Let's use the C actually here, because we're talking about units. Yeah. So coulombs cancel out, you're left with joules per second, which of course is watts, right? So that's your power rating and so on. So again, just try to keep track of these equations based on what they mean, rather than just memorizing formulas and the letters. Right? That's a tip to help make this easier for you. So that's it for now. Thanks for watching, and as always, subscribe and so on. Help spread this resource around to other physics students. All right, talk to you later. Bye.